In this video, we are going to discuss about how to name coordination compounds. Okay, we'll start with positive complex. So this video mainly we discuss the general rules and plus how to name positive complex. Okay, so I hope you know like the basic idea about complexes or coordination compounds, right? So basically, what is a complex or a coordination compound? Compounds containing coordinate bond, right? Compounds containing coordinate bonds are called complexes. Okay. So what is a coordinate bond? Remember, a coordinate bond always forms between a Lewis acid and a Lewis base. Okay. The Lewis acid means they are electron pair donors. Electron pair donors. So they have free electrons with them. Okay, so they can donate. Lewis acids mean they are electron deficient, so they tend to accept these pairs. So they are electron pair acceptors. Electron pair acceptors. Okay, so one is having free electrons, other is deficient of electron. So they can donate to the those who requires that electron pair, Lewis base donate electron pair to Lewis acids. So those who donate we call in coordination compound we use certain terminologies. So those who donate we call ligand. Okay, those who accept we are studying about coordination compounds or transition metals. So here the metal will be the act as metal ions or metals will be act as a Lewis acid. So the metal ions okay will be accepting the electron pair from the ligand. Okay. So remember coordination compound in transition metal complexes. Okay, the ligand will be either any negative charge species, okay, or species having free electrons. Okay, that's our ligand. Either negative charge species or species having lone pairs can act as ligand, and the Lewis acid will be the metal ions or metals. Okay, because they have vacant orbitals, d orbitals. Okay, so they can accept a pair. Okay, like they can accept the pair of electron donated by the ligand to their orbitals. That's how coordinate bond will form. Okay, now how to understand which is the coordinate bond. Okay, so whatever is written inside the square bracket, that is always coordinate bond. So you can see here CONH3 6 times is written inside the square bracket, which means the metal cobalt is surrounded by 6 ammonia ligand. 6 ammonia ligand. Okay, we know ammonia is a Lewis base because they have a lone pair in nitrogen. So this lone pair can give to that metal orbitals, okay, for sharing. It's sharing on, it's not transferring, it's sharing, but both electrons are given by one entity. So it's not a pure covalent bond. It's covalent, but it's both electrons are donated by one species. So we call it a different type of covalent bond. It's called coordinate bond. So 6 nitrogen is donating its electron pair to the like metal. So there are 6 coordinate bond. Okay. So this is the coordinate part. Okay. Now you can see like there is some other species outside the square bracket that's we called counter ion. So here the counter ion is 3Cl. Here the counter ion is 2 potassium. Remember, if you put any complex in water, it splits here. Only the counter ions, okay, like the whatever inside the square bracket, that bond never breaks. So here the CO ammonia bond, the 6 CO ammonia bond never breaks if you put in water. Okay, but only the outside this coordination sphere they breaks. So the counter ions will be going into solutions and the complex become the whole complex also become like corresponding ion. Okay, clear. So always remember this is very important, the counter ions whatever is outside the coordination sphere it's called counter ion. Okay, so if you put this in water you'll get 3Cl minus. If you put this complex in water you'll get 2K plus. So it breaks outside the coordination sphere, outside the sphere. Okay, outside the square bracket. whatever inside is never breaks in solution. So coordinate bond is highly stable in aqueous solutions. They won't break in aqueous solution. Okay. Now, how to name complexes? Okay, so it's different rules for like different complexes. So we are going to discuss about only the naming of general rules as well as naming of positive complex. Okay, so how to decide that whether the complex is positive or negative? It's very easy. Okay, so whenever writing any compound, say sodium chloride, okay, or aluminum chloride, okay, whatever be the compound, whatever we written first is positive, second is negative, right? Aluminum 3 plus 3Cl minus. Okay, so whatever is written first will be the cation and second will be the anion. Okay, so here you can see there are two parts. So here the square bracket is the first part, so that is positive. The Cl3 is a negative part. So here, since the coordinate part is positive, we can call it positive complex. So this is a positive complex. So how to understand that the complexes are positive or negative? So if you see the square bracket as the first term, okay, it's positive complex. Now look at the second example. Okay, here the first is written is K2, potassium. Okay, so this is the plus positive part. Okay, so the square bracket is coming in the second term, second part. Okay, so this is a negative part. So this is a negative complex. Okay, so you can decide whether a complex is positive or negative depending upon where the square bracket is placed. If the square bracket is written first, and followed by some counter ions like Cl or something, this is a positive complex. If you have already one positive part is there and the square bracket is coming as a second term, it's a negative complex. So that's a basic idea you need to have. Okay, I hope it's clear how to understand that whether the complex is positive or negative. Okay, we'll move on. Now, what is the first rule? Okay, suppose when you write NaCl, okay, you'll always name it sodium chloride, not chloride sodium, right? So the basic rule is always name positive part followed by negative part. So sodium chloride. So whatever is coming first, you have to name that. Okay, that's the first rule. Okay, for example, here the first part is the complex. Okay, so here you have to name the complex first. Name the complex and then like the second part. Okay, so here the first written is potassium, so you have to start with potassium. Okay, and then name the complex. So always remember, name whatever is written first, you have to name that. Okay, got it. Now if you name whatever is like, if you see the square bracket, that's a coordinate bond, right? What all things will be there inside the square bracket? You have a metal and you have a number of ligands. Okay, maybe same ligand or different type of ligand. So multiple ligands is possible. Okay, so you have metal as well as different type of ligand inside the square bracket. Always remember, when you're writing a, when you're naming a complex, okay, that is whatever is written inside the square bracket. Okay, the rule is that always name the ligands first. So while naming complexes part, whatever is inside square bracket, you have to name ligands first. Then only metal. So finish the ligands naming, then go name the metal. Okay. So whatever is written inside the square bracket is called coordination entity. Okay. So inside the coordination entity, you will find metal as well as ligand. Always name ligand first, then followed by metal. So first ligand, then metal. Okay, clear. That's a second rule. Okay. Now, if you have more than one type of ligand, so look at the first complex. So all the ligands are NH3. That is only one type of ligand. Okay. For the second example, you have two ligands, right? You have NH3 as well as Cl. So whenever more than one type of ligand is there, okay, you should follow alphabetical. So which one to be named first? So you have to follow alphabetic order in such cases. Alphabetical order. Okay, how to name the ligand, so that we are going to see. But remember, if more than one type of ligand is present, okay, you have to follow alphabetic order. Okay, whoever is coming first in alphabetic preference has to name first. Okay, So suppose if NH3 is coming first, name NH3 first, then chloride, then metal. Okay, like that. Clear? So that's a rule. While naming ligands should follow alphabetic order. That's the second rule. Okay. Now there's a very important rule. So we know a ligand means either negative charge species or species having lone pairs, free electrons, right? So both are ligands. So for a negative charge ligands, if you look at all the negative charge ligands, you'll find something common in them. Okay, their name will end up with E, right? Chloride. If you name Br minus, bromide. If you name like Cn minus, cyanide. So remember, like any negative ligand, okay, its name going to be end with E. Okay, so if such ligand comes, okay, a negative ligand comes, how to name the ligand? You should remove that E and add the suffix O. Okay, so if Cl minus is present as a ligand, you should name it like chlorido, chlorido. Remove E, add O, chlorido, bromido, like that. It's a very, very important rule. For negative ligands, remove E from their name and add the suffix O. It's a revised naming. If you check some old videos or like old textbook or gates, you might have seen chloro, bromo, like that. Okay, that's not like nowadays we are not using it. IUPAC has revised it. So remember, so just note that change. If you're using any old textbook or guide or old videos, now you'll see chloro, bromo like that. It's revised. Now it's chlorido, bromido like that. So we'll see some important ligand and how to name that. Okay. So you can see all these are negative ligands. Okay. So all their names are ending with E. Okay. Cl minus. So remove E. How to name? Remove E, add O. Chlorido, okay, bromide, bromido, iodide, iodido, hydroxide, OH minus as a ligand, hydroxido. When cyanide comes, cyanido, okay. When like cyanide is an ambidendate ligand. So this is an important example, cyanide, okay. Cn minus means, remember the minus is on carbon. So carbon can donate, okay. So then we use cyanido, okay. We know there is a lone pair in nitrogen, right? So nitrogen can also donate electron to metal. So when nitrogen donate, okay, we like isocyanate ion, okay, Nc minus, isocyanate ion, okay. So in that case, we use isocyanide, okay. Now SO for 2, remember their charges, okay. The charge carried by the ligand is very important that we use to find the charge of the metal. So that has to be noted, that has to be remembered. Sulfate, a very common ion, sulfate. So sulfato. Oxalate, remember oxalate. Oxalate is coming from oxalic acid. Oxalic acid is COOH, COOH. When it dissociate, it remove H plus. So the remaining part we call oxalate ion. Okay. COO minus, CO minus. Together we write C2 for oxygen O4 with 2 negative charge. So this is oxalate ion. So we use remove E, add O, oxalato. Carbonate become carbonato. So remember sulfate, oxalate, carbonate, all these carry 2 minus charge. Okay. Then SCN minus. This is also an ambidendate ligand. Okay. So here SCN minus means actually the negative charge is on sulfur. Okay. So here sulfur is a donor. Sulfur can donate electron pair to metal. Okay. So thiocyanate ion. Okay. So there is a lone pair on nitrogen that can also donate. If nitrogen donate, we write like NCS minus. So it's called isothiocyanate ion. Then we use isothiocyanate too. So ambidendate ligand is a very important topic. So just study what is ambidendate ligand now, like some examples for that. Okay. Now, if you see another ambidendate ligand, NO2 minus, okay. So NO2 minus, the structure of NO2 minus is like this: N double bond O, coordinate bond O minus. This is the structure of NO2 minus. Okay. This is also an ambidendate ligand. Okay, where oxygen, the negative charge on oxygen, it can donate, or then there is lone pair on nitrogen that is also donate. So there are two possibilities. Two atoms can donate. Okay, in both nitrogen and oxygen. Okay. So if oxygen is donating, so it's a negative ligand, right? NO2 minus, it's a negative charge. So remove E, add O. So when you name it nitrate O, but who is the donor? If oxygen donate, we write, to address that oxygen is a donor, we write nitrito hyphen O. If N is donating, we write nitrito N. How to understand that who is donating? So when you write the complexes, okay, look at this. So here it's given as NO2. So if you're writing NO2 inside the square bracket, okay, you should assume that N is donating. N is the donor. N is donating electron to the vacant orbitals of metals. So in that case, we use, again it's a negative ligand. So remove E, add O, nitrito. And N is donating. So nitrito N. How you understood that N is donating? Because it's written NO2. Suppose O is donating, we write like, you will see ONO in the parenthesis. If you're seeing ONO inside the parenthesis, still it's NO2, but oxygen is donating. Okay. So in such case, we write nitrito O as the name of the ligand. So it's important. Okay, just note that also. Okay. It's an ambidendate ligand. So who is donating is important. Accordingly, the name will change. Okay, clear? Now, so we just saw some negative ligands. Now there are some neutral ligands, okay, having lone pairs with them. Carbon monoxide, that's the strongest ligand. So out of all the ligands, this is having the a greater tendency to form coordinate, the strongest ligand. More stronger coordinate bond will form by CO. Okay, so what is the name of? We use the name of the group as such. Okay, it's carbonyl group CO. It's a ketonic group, right? C like carbonyl group. Okay, now En. En means, okay, it's actually an organic ligand. It's an organic ligand. How to expand this? En means ethane 1,2-diamine. What is ethane? Ethane is CH3, CH3. So 1,2-diamine means we are replacing one hydrogen from ethane, both first and second carbon, we replace one hydrogen with NH2 group. So this is ethane 1,2-diamine. Okay, it's a bidentate ligand because there are two nitrogen atoms, both can donate to the vacant orbitals of the metal at a time. So it's a bidentate ligand. Okay, so whenever you see En, remember it's a short form of ethane 1,2-diamine. This is IUPAC name of the compound. Okay, ethane 1,2-diamine. So nowadays, in coordination compound, we use for organic ligands, we use IUPAC names. Earlier, we used to have common names. So if you check some old textbook or guides or old videos, okay, you will see this is maybe they use ethylene diamine. Okay, ethylene diamine. So it's revised now. So now we are no longer using the ethylene diamine. We have to use ethane 1,2-diamine. Okay, clear? So then NO means nitrosyl group. Pyridine. Pyridine is like kind of like benzene ring, but there is only 5 carbon. The sixth one is nitrogen. Okay, so this is pyridine. Okay, so it's having a lone pair on nitrogen, so it's also ligand. It's an organic ligand again. Pyridine. So if you see PY, your name pyridine. Okay, so remember CO carbonyl, En ethane 1,2-diamine, NO nitrosyl, PY pyridine. And we also use some special names. Okay, so whenever H2O, we know there are two lone pair on oxygen. Okay, so it can donate. So it's a ligand. So when H2O is acting as a ligand, we use the term aqua. To address the presence of H2O, we use aqua. When ammonia, okay, it's a Lewis base, right? It's having lone pair on nitrogen. So when ammonia is acting as a ligand, we use not amine, it's amine, double M. Okay, remember, not amine, it's amine, double M is the amine. Okay, that's also very, very important ligand. Okay, now if you look at this complex, you have a cobalt is a metal and the ligand is ammonia. How many ligands are there? 6 ligands, right? So how to address that there are 6 ligands? So the presence of NH3 we address with using amine, right? Amine, but there are 6 amine. Okay, so to address when there is more than one ligand is present, we use certain prefixes to address their proper number. Okay, if there is 2 ligand, we use di. Okay, suppose if there is 2 NH3, we use diamine. Diamine. If there is 3, we use triamine. Okay, So we use the prefixes, suitable prefixes, di, tri, tetra, penta, hexa, like that. Hexa. Okay, so this is hexa. There are 6 NH, right? Hexa. Okay, then amine. Hexa amine. Okay, so we have to name the ligand first. There are 6 ammonia, so hexaamine. Okay, so once we finish the naming of ligand, okay, then what left in the square bracket? That's cobalt. Okay, so in positive complex, okay, in positive complex, we use the name of the metal as such. Okay, we'll come back to this example. Okay, so remember, like in positive complex, we use the name of the complex as such. Okay, so this naming will be like there are 6 ammonia, right? Hexamine, cobalt, like that. Okay, so if you see this example, okay, you have 2 chlorine, right? So dichlorido. Okay, now there are 2 en. What is en? En is ethane 1,2-diene. It's not a simple ligand, right? It's not a simple ligand. It's a ligand with, it's an organic ligand with numbers and all. So we treat it as a complex ligand. So if a ligand having numbers and all, okay, we treat it as a, it's not a simple ligand. So we call it a complex ligand. It's a complicated ligand. Okay, for complicated ligand like En, okay, we won't use this di, tri, tetra and all. Instead of that, we use some other prefixes. Okay, remember this is very important. If mainly when we use En, okay, if there is 2 En twice, we won't say di. Okay, we have to use bis. So for 2, instead of di, we use bis. So when to use bis? When the ligand is a complicated ligand with numbers and all. Okay, so for tri, we use tris. For 4, we use tetrakis, pentakis, like that. Okay, so this is only for complicated ligands, mainly for En. Okay, clear? So here you can see there are 3 En, right? So we won't use triethane 1,2-diene. That's wrong. Okay, you have to use tris. Okay, so when we use bis tris, the next thing should be open the parenthesis, write the name of the ligand. So ethane 1,2-diamine. So this is also important. Whenever you are naming a complicated ligand, we have to use bis tris tetrakis, like that, for 3, 2, 3, 4. But in such cases, okay, you just write bis or tris. The next should be open a parenthesis. The ligand name should be inside the bracket. Okay, like this. Okay, so you can see here this presence of En should be addressed as not with tri. That's wrong. Okay, should use tris. So tris, then open the bracket, name of the ligand. Okay, it should be enclosed within the parenthesis. Clear? Okay, now the last rule and the most important rule. Suppose the complex is a positive complex when the square bracket is first. Okay, so how to start? When naming coordination part, always ligand first. Okay, so we start with there are 6 ammonia. So hexa, ammonia is named as amine, hexaamine. Then what left in the square bracket? Metal. What is a metal? Cobalt. For positive complex, we use the name of the metal as such. So hexaamine, cobalt. Okay, whenever you're writing a metal, the next thing should be the charge of the metal should be written in in a parenthesis in Roman letters, like 1, 2. If it is +1 charge, we use a Roman letter 1. If it is +2 charge, we use Roman letter 2. If it is +3 charge, we use Roman letter 3, like that. Okay, clear? So how to find out the charge of the metal? Okay, so to find out the charge of the metal, okay, you should start from the counter ion part. You should think like how this complex will split in solution. Okay, so if you put this complex in water, how it splits? So always I told it splits outside the complex, like outside the coordination sphere, outside the square bracket. Okay, so if there are 3 Cl outside, so if you put in water, the 3 Cl will go to solution as 3 Cl minus. Okay, so what remains? CO NH3 6 times. Okay, what is the charge of the, suppose if you split NaCl, okay, how it splits like Na plus and Cl minus. So whatever negative charge is there, that should be balanced by the positive charge. Okay, so here the counter ions having 3 Cl minus, like Cl minus, Cl minus, Cl minus. So what is the total charge of the counter ion? Minus 3. That to be balanced by the complex. So what is the charge of the complex? Plus 3. So how to find out the charge of the complex? That you have to find by looking at the counter ion. Suppose it is Cl2, the charge of the counter ion will be minus 2. So complex will be plus 2. Okay, like that. So what will be the charge of the counter ion? That to be balanced by the complex ion. Okay, so this is the most important thing. You have to find out the charge of the metal. You have to find out the charge of the like complex. Okay, so what is the charge of the complex here? The charge of the complex is plus 3. How I got the charge of the complex is plus 3? From the counter ion, because the counter is Cl3. So 3 Cl minus will go to water. So the charge, total charge of the counter ion is minus 3, balancing plus 3. Okay, so remember this plus 3 is a charge of the whole square bracket, which means that includes metal, charge of metal plus charge of ligand, total. Okay, now what is the charge of metal? Okay, that we don't know. X. What is the charge of ammonia? Ammonia is a neutral ligand, so no charge. So 6 into 0, no charge. What is the total charge of the complex? Plus 3. So what is H plus 0 is plus 3. So what is the charge of metal then? Charge of metal is plus 3 itself. Okay, so the charge of the total complex is plus 3. So since there is no contribution, no charge from ammonia ligand, the plus 3 is purely belong to cobalt. So the charge is 3. Okay, how to write that? You should write the 3 in Roman letters in parentheses after naming metal. Okay, so how to name this? So this is a positive complex. So always in complex, start with ligand. There are 6 ammonia. So hexaamine, hexaamine. Okay, now after finishing ligand, metal. So cobalt. Now charge of the, whenever writing metal, the next thing should be open a bracket and write its charge. How to find out the charge? From the counter ion. So this is minus 3, this is plus 3. No charge from ammonia, so it's cobalt 3. Now what left? The negative part. What is the negative part? Chloride. So what is the name of the complex? Hexaamine cobalt 3 chloride. Remember, this is very important. Like, okay, don't worry about this subscript on the like outside the coordination sphere. Okay, whether it is Cl or Cl2 or Cl3, this number doesn't matter in naming. Okay, so the subscript of counter ion is not important at all. Okay, so that number of the counter ion doesn't. So when we write AlCl3, how you name this? Aluminium chloride, right? You won't say aluminium trichloride. Okay, so this number is not important. So simply you say whether if it is outside is Cl or Cl2 or Cl3 or Cl4, whatever it is, you simply say chloride. No need of that subscript, no need to give importance to the subscript number to the counter ion. So the name is hexaamine cobalt 3 chloride. That's it. Okay, clear. Now we'll see some examples. Okay, so remember, for positive complex, we have to use the name of the metal as such. Okay, same name, no need to change anything. Whatever be the name of the metal, we use as such. But negative complex, okay, the rule will change. Okay, so that time we'll discuss in the next video. So remember here we use if it is gold, like AU, we use a gold as such. If it is tin as such, Ag silver as such, Fe iron as such. So for positive complex, the metal name is the original name, okay, to be used. Okay, now I'll see how to name this. Okay, so already we did this. What is the name? So start with ligand. Inside the square bracket, start with ligand. Okay, so 6 ammonia. So hexaamine, double M. Okay, amine. Then what left inside the square bracket? Metal. What is the name of the metal? Cobalt. So once the metal is written, the next thing should be charge. Okay, what is the charge? That to find out from the counter ion. So counter ion is Cl3 minus 3 outside. So plus 3 on the complex, but there is no charge from ammonia. So plus 3 is for the charge of metal itself. So cobalt 3. Now what left? The negative part, chloride. Don't write trichloride, simply write chloride. Okay. Now do the second one. Okay. So this is the coordinate part. It's a positive complex. So there are two type of ligand, right? One is NH3. How to name NH3? Amine. Then Cl you have. So Cl is a negative ligand. So remove E, add O, chlorido. So alphabetic preference A, B, C. So preference go for amine. So how many amine? So pentaamine. So pentaamine. Always remember it's a name. So the first letter to be capital and no gap in between. So it's continuous. Okay. Pentaamine. Then the second ligand, chlorido. Then what left in the square bracket? Metal. So what is it? Cobalt. So once cobalt is written, then write their charge. So how to find the charge now? Okay, it's very easy. Look at the counter ion. Okay, what is the counter ion here? It's Cl2, right? Cl2 means, so if you put this complex in water, it splits here. Okay, so this Cl2 will go to as 2 Cl minus ions. So Cl minus, Cl minus. Okay, so -2 is the charge of the counter ion. So it should be balanced by the complex. So complex charge is +2. So +2 is the total charge of the complex. Okay. So +2 is the total charge of the complex. So total charge of the complex means the complex contain ligand plus metal, right? Suppose metal charge is X, unknown. Ammonia doesn't have any charge, so no contribution, so 0. Steel has -1, so -1. Total charge is +2. So X minus 1 is +2 or X is +3. So what is the charge of cobalt? It's 3. Okay, otherwise also we can simply find from this. Okay, the total charge of the complex is +2. Ammonia has no charge, Cl is -1. So 3 minus 1 is 2. Okay, so cobalt 3. What left? Chloride. So it doesn't matter what is Cl3 or Cl2 or Cl or Cl4 outside. Always don't think about that, bother about that number. Just write chloride without using that number. Okay, don't say dichloride, trichloride, simply say chloride. Okay, clear. I will see more examples. Now, how to name this? So the ligand first. So aqua, it's water, right? It's a special name, aqua. So how many aqua? 6. So hexa, aqua. What is the metal name? Manganese. Manganese. Okay. Now what left? Once the metal is written, S should be charged. So how to find out the charge? Look at the counter ion. The counter ion is 2 minus. Sulfate, right? SO for 2 minus. So that to be balanced by 2 plus. So what is the charge of the complex? 2 plus. But we know there is no charge for water. So this 2 plus is charge of Mn itself. So manganese 2 sulfate. Negative part, sulfate. Okay, that's it. The next one, there are 2 ligands, right? You have amine, you have Br minus. Okay, bromide ion. So bromido. So alphabetic order, amine will get preference. So how many NH3? 5. So pentaamine. Pentaamine. Okay, then bromido. Then what left? Metal. So cobalt. Once metal is written, then the charge inside the parenthesis. Okay, how to find out the charge? Okay, from the counter ion. Okay, so what is the counter ion? The counter ion is, you don't worry about this 2H2O. Anyway, H2O doesn't have any charge. So just focus on the counter ion. It's -2. So balancing +2. So +2 is the charge of the whole complex. That includes metal charge X. Ammonia has no contribution, so 0. Br has -1, so total charge is +2. So X will be +3. Okay. Otherwise, also you can think 3 minus 1 is 2, right? So it's cobalt 3 sulfate. Cobalt 3 sulfate. Now what else? There is 2 dot H2O, right? So whenever you're writing like some what we call is water of hydration, right? CuSO for 5H2O. It's called water of hydration. Okay. So we use like how many water? 5 water. Okay. Here it is 2 water. So we write dihydrate. So after writing sulfate, add it dihydrate. So whenever any names, okay, you are seeing like 1H2O, 2H2O, 3H2O. So it's treated as water of hydration. Okay. So we say normally we use monohydrate, okay, dihydrate, trihydrate, like that. That will be the name will be ending with the hydrate. Okay. If it is half H2O, we say hemihydrate, half H2O, hemihydrate. So this is important. Okay. So whenever H2O is coming after the name, use hydrate for water. It's not a ligand now. Ligand is when it is coming inside the square bracket. This is outside. It's like it's inside the crystal. Okay, it's not a ligand. Okay, so it's treated as water of hydration. So like you use dihydrate, hemihydrate, monohydrate. Okay, like that. Understood. So if it is 3H2O, trihydrate. If it is 4H2O, tetrahydrate. If it is 5H2O, pentahydrate, like that. Okay, clear. Now, look at this. So I use this example to to make you know that how to name ambidentate ligand. So you can see there is an ambidentate ligand, NO2, right? So see the difference in this. So there are how many ligands are there? 3 ligands. So always name the ligand first, alphabetic order. Okay, you have amine, you have chlorido, you have nitrite. Nitrite is a negative ligand, right? So nitrito. Now it's written NO2, right? Which means N is a donor. So how to name then? 4-amine, right? So tetraamine, tetraamine. Okay. Then chlorido, alphabetic order, chlorido. Only one chloride, so simply chlorido. Then you have a nitrate ion, so nitrito. So it's written NO2, which means N is donating. So put hyphen and write N, which means N is donating. Okay. Now what left? Cobalt, nitrito N, cobalt. So what is the charge? How to find out the charge? Okay, look at the outside the coordination sphere. So outside the coordination sphere, what is written? Cl, right? Only one Cl, which means if you put this in water, it splits here. -1 is outside the charge. What is the charge of the complex? +1. Okay. So +1 is the total charge of the complex. So ammonia doesn't have any charge. Cl have -1. Nitrite ion has -1. So something -2 is +1. So something -2 is +1. So what is the unknown charge? Charge of metal is 3 - 2 is 1, right? So it's 3. So cobalt 3. Cobalt 3. What left? Chloride, the counter ion, chloride. Okay, that's it. So if you come to this, what is the only change? Instead of NO2, it has written ONO here. So the same ligand NO2, right? But it's written ONO. This is indicate that the donor is not N, it's O. So the only change here is instead of nitrito N, we use nitrito O. That's the only change. Rest everything is same. Tetramine, chlorido, nitrito. Instead of N, it's nitrito O. Okay. So how it is possible? Because it's an ambidentate ligand. It has 2 donor atoms. Okay. So if you are written NO2, okay, remember N is a donor. If it is written ONO, O is a donor. So I will address by writing like this: nitrito N, nitrito O. That's it. Now we'll see some examples with EN. Okay. So look at this. So how EN is important? It's a complicated ligand, right? Ethane 1,2-diamine. Ethane 1,2-diamine. Okay. For a complicated ligands, like what we use, we won't use di-tri. Instead of that, we use bis, tris, like that, 4, 2, 3, and all. Okay. So just to familiarize that. So here 2 ligand, right? One is chlorido, one is En. So A, B, C, D, E. So C get preference. So how many Cl? 2 Cl. So it start with, always first letter is capital. So dichlorido. Then what? Next is En. Ethane 1,2-diamine. Okay, it's a complicated ligand. So we cannot use di. We have to write bis. Instead of di, write bis. Once you written bis, open a bracket, write the name of the ligand. So ethane 1,2-diamine. close the bracket. Then what left? Metal. So chromium. Once the metal is written, the next thing should be charge. Okay, what is the charge? It's no gap, continuous. Okay, chromium. What is the charge? How to find out the charge? What is outer counter ion? Okay, counter ion is Cl. So -1 is outside the charge. Charge of the complex is +1. Okay, En doesn't have any charge. Only Cl has charge. So there is Cl2, right? -2 for 2Cl. So some unknown -2 is +1. So it's very clear. 3 - 2 is +1. So chromium 3. Charge of chromium is 3. So chromium 3. What left? Chloride. That's it. Now here, how it different from the rest of the examples? Here only a coordinate part is given. The negative part is not given. Okay. So if it is not given, you don't need to write it. That's it. Okay. So don't get upset with that. So here just remember it's only the ion is given. The positive complex ion is given. Okay. So whatever is given, you name that. That's it. Okay. So here we'll start with again the same thing, right? It's like dichlorido. So when you compare the first and second example, okay, what is the difference? The difference only here the counter ion is given. Here the counter ion. Suppose if you remove the Cl, what left? It's plus, right? So the Cl is not given here. That's it. Okay, so you can just avoid that term chloride. That's it. Okay, so how we name this? Same thing, dichlorido. Everything is same. Dichlorido. En. So bis. What is the name? Ethane 1,2-diamine. Ethane 1,2-diamine. Okay. Now, like what left? Cobalt, right? So sorry, the metal is different. So cobalt. Okay. Cobalt. What is the charge? Total charge of the complex is +1. Plus means +1. Okay. So En doesn't have any charge. Cl is -2. So 3 - 2 is 1, right? So cobalt 3. Okay, cobalt 3. Here the negative part is not there. So it's an ion, right? A plus charge. So simply write cobalt 3 ion. That's it. Okay, since the counter ion is not given, you simply write it as an ion. So dichloride of bis, ethane 1,2-diamine, cobalt 3 ion. Okay, hope it's clear. So if you understand this naming of negative source is very easy. Okay, so in the descriptive box, okay, I have given like you can practice. There is 35 practice questions is given along with answers. Okay, you just click on the link and you can download and see. So I'll give in 2 different files. Okay, so both link will be attached. You'll get the worksheet first. Okay, so try it your own. Okay, and then you can check the answer from the second one. Okay, so I hope it's really helpful. If you find it helpful now to like I'll be coming with negative complex and neutral complexes soon. Okay, so please do support, subscribe and share. Okay, thank you so much.